Okay, so one of the aspects that we had talked about earlier this week, or I guess yesterday, is that when it comes to impending weather, like what we may have this week, chances are what's going to happen is at some point this afternoon I will run off your first problem solving sheet for this chapter, and it deals with dot diagrams. And what you see up here on the board is where we had left off with yesterday. Okay, and we'll continue with that. And uh, I think what could happen, I don't know what the weather's going to happen with tomorrow. We could have a late start, and should that happen, we would not have class tomorrow. Okay, and rather than trying to draw this information all at once as you return from school, okay, if we have the information needed, even when you're at home, to go to the Science Channel and see some examples that we would possibly be going over in class, you would have that information to keep continuing forward. Remember, Friday, we have some vocab terms that are due. I see some of you working on them, and that is fine. So let's go ahead and pick up where we had left off with yesterday. And this comes from this formula, H2SO4. Okay, so we've dealt with our sulfur. How do we know that? When you're looking up at this dot diagram, how do we know that sulfur is done other than it's written up already? It's got 6 dots around it because sulfur is in what column? The 6th one. Remember, the column, with the exception of the transition metals, tells you how many valence electrons are present. Okay, so 6 dots, column 6. So we've taken care of 2 oxygens. Okay, so notice we have an unshared pair of electrons like what we do there. These are sharing between the sulfur and the oxygen, and that's what we call a covalent bond. Okay, and the difference between that is we had shown you an example of an ionic bond. Okay, and that was this example. We'll never think of that young lady the same, and don't make that young lady upset, because potassium chloride is kind of not a nice compound to have inside of us. Yeah, in a specific amount, of course. So the reason we call this an ionic bond is typically, you could say, it's between a metal and a non-metal. Okay, metal and a non-metal. How do we know that potassium is a metal? It's in the first column. So you can safely say, looking at your table or over here on this one, that metals typically are what color on that table. Okay, and that's fine, but when we're looking at, and we can all see that, what color do we know all metals are on this big periodic table? Those would be synthetics. Blue are liquids. Black lettering. Okay, so all of these, from lithium and sodium in column 1 to rhodium to cobalt to cadmium to zinc to gallium to tin to antimony, polonium, okay? Those are all solids, would be a better way of looking at that, but most of them are metals then, okay? If it's written in red, it is a what? It's a gas. Column 8 is a noble gas. So it's safe to say that if it's written in black, that it's a solid, and for the most part, they're probably metals. Not all of them, because sulfur is a solid, but it's obviously not a metal. It's near that zigzag line that we call metalloids, that kind of really can't make their mind up if they want to be a metal or a non-metal. Okay, so in this case, this is a clear evidence of an ionic bond, because chlorine now is stable. It's Why is chlorine chemically stable now? That's what this box is illustrating. It now has 80 electrons in its outer energy level. So, potassium doesn't have any around that. But that's okay, because metals want to do what with their electrons? They want to get rid of them. So they don't want anything around them. Okay? So that is, again, an example of an ionic bond. So, when it comes to what we see here, okay, these are non-metals so far. So what can we safely say about oxygen? Is it that atom's outer energy level? Is it full? This one has how many total? Yeah, so this oxygen is now chemically stable. Okay, so is that top one. So we've dealt with 2 of our oxygens, so we've got 2 left, so we can put one here. Okay. But what could possibly be a problem with putting one here and one here? What do we notice about both of those oxygens that are written in black? Do they have 8 electrons around them? No. But what element have we not dealt with yet? We see 1 sulfur here. We see our 4 oxygens. But it's kind of like either being behind or being tied going into the bottom of the 9th here. You still have 1 at bat left. Okay? So we still have 2 hydrogens to contend with. So if this is 1 electron short, where's it going to grab it from? And what a coincidence. What column is hydrogen in? It's in the first one. So it has how many electrons to give away? Then what about this side? Same thing. Okay. Now, you can draw boxes around each. Well, that's not quite a box. But for the most part, you don't have to do this, but sometimes it's easier to see. Now, each and every one of those atoms has how many electrons around them, with the exception of hydrogen. They all have 8 electrons around them. So why doesn't hydrogen have 8 around? Because for one thing, it can't have that many. What's another reason? Yeah, it got rid of its lone electron. Such a nice guy, it gave it away to the oxygens. Okay, so this is an example really of an ionic bond because you have metallic-like characteristics of hydrogen donating or giving away its electrons to that of the oxygen. Okay. And one of the aspects you could be looking at that and say, well, how do you know which element to start with when you're doing these? Okay? A good rule of thumb is look at it this way. Always put carbon in the center, nitrogen if the carbon's not present, okay? And then put metals in the middle, okay? But when it comes to an atom that's this complex, okay, even though these are both in the same column, choose the one that only has 1 atom of that formula, and that's why it's sulfur. So, using that logic with what we just said, when it comes to an acid like this, how do you know what to start with, the hydrogen, the sulfur, or the oxygen? We would choose sulfur because there's only 1 atom with that rather than 4 with that of the oxygens. So, should you see an example of phosphoric acid then, where we would have this? Which atom do you think would go in the center, the oxygen or the phosphorus? The phosphorus would, okay? So some of the general rule of thumbs that we want you to follow, put carbon in the center if it's present, and if that's not present, well then use a metal. Well, really don't have that either, but since there's one atom of this, you would put the phosphorus in the middle, okay? Because one of the things that human nature is going to make itself known is someone's going to put a sulfur here, going back to this example. They're going to, for instance, put an oxygen on there, and then they're going to put another oxygen over here, and then another oxygen, okay? That's not how that molecule would look like, or that compound. Because when we get further down in the semester how some of these compounds react, it's the hydrogens that have to be stripped off of there. And it can't do that unless it's way out on the edges like what it is here, okay? So when it comes to formulas like this, we choose sulfur because there's only one atom. We choose phosphorus because there's only one atom. And it'll look almost exactly like this. Very similar. This compound would look very similar to that one, other than phosphorus would be in the middle. You got your 4 oxygens, and then 3 hydrogens would be surrounding that that compound. Okay. So those are examples of ionic bonds where electrons are completely transferred. Well, remember, to become chemically stable, these molecules or compounds want to have how many electrons around them? 8. So that's why we call it an octet rule. Okay? So when we're talking about an octagon or stop signs, that's why you see 8 sides with an octagon. So the octet rule means you want to have 8 electrons as well. But what happens when you're dealing with very simple molecules like these? Remember, we said this only about once or twice yesterday. And we'll find out next chapter when it comes to chemical reactions who actually, I wouldn't say remembers because there's probably a lot to remember, but was actually listening. When we talk about those top 2 examples, chlorine and iodine, I think someone might remember what we called those yesterday. They're a specific type of molecule. Starts with the letter D. Diatomic. Those are diatomic molecules. Okay? Which means they don't exist in nature alone. So halogens are diatomic, which these 2 are. Other substances are also diatomic, like gases, like hydrogen. What else? Oxygen's diatomic. There's one more. We said hydrogen already. Nitrogen's the other one. That's also diatomic. Okay. So when we look at these 2, okay, we'll go ahead and put a chlorine here. Chlorine atom. Okay? And from what we just did earlier, what column is chlorine in? The 7th one. So dots, E's, X's, whatever. We'll choose X's. And how many short is that chlorine atom from becoming chemically stable? 1, because it only has 7, right? Okay, well, but don't write this next part down yet, okay? So if we take another chlorine atom, okay, and do this, how many short is that one? Also 1. So if you were drawing this in Microsoft Word or whatever, where you're picking something up and transposing it, you maybe click on it with that little hand or the mouse, you pick it up, and let's move it to up here. And that's what we would do. So now you can draw that. We're picking this up and moving it up here. Oops, I didn't mean to do that. It was a triangle. Okay? And then these here, rest of these triangles. So, do you think that we've satisfied the octet rule? The answer is yes, because we've created a single bond between these 2. So we can take a box and draw it around here. That chlorine has got how many? 8. Okay? We can also do, and you don't have, there's students who continue to do this all the way up to the exam, and that's fine, but you don't have to. We can also show that this chlorine atom has got 8. Inside each one of those boxes, there's 8 electrons around them. And that's how or why we arrive at being a diatomic molecule, because these 2 electrons are being shared between those 2 chlorine atoms. Okay? So they are now both chemically stable. So, does that look like a covalent bond or an ionic bond? What does it mean to be an ionic bond? Well, yeah, but that isn't that which would not be an ionic bond, but rather covalent. So how did we illustrate an ionic bond? Why did we use yourself as an example? A little more specific. We said it's safe to say that as you're looking at that periodic table, you would want to use not necessarily just a solid, a metal and a non-metal. That's right. But what about if you have 2 non-metals? Well, that's what chlorine is. Those are both non-metals, and those electrons are being shared. The reason that we can tell the difference is, what did that potassium do? It didn't have any electrons around it, did it? Because it completely transferred that electron away. Again, these are being shared. It's not a complete transfer like what we saw this being. And we just drew this up there not too long ago. That is an ionic bond. It was a complete transfer between the 2. Okay, so if we just did chlorine, how would iodine be different? Or would it be the same? Because what column is iodine in? The 7th. It's in the same column as what? So the only difference between this and this, you wouldn't even have to do the whole thing over again. We can just erase the Cl's and put what in there? Yeah, you can just put an I here and an I here. It's the same thing. And we can safely say that because iodine and chlorine are in the what? The same column. So they'll have very similar properties. Okay. Is anybody lost with these diatomic molecules? Left outside, we're on the bus. Left middle, middle, right middle. Okay, right outside. Okay. So we are all nodding our head yes, so you're telling me that we understand this so far, which is good. Okay. So now when we look at these, we said, how do we know what to put in the center? Well, of these 2, which one's going to go in the center? Yes. Not S-I, and was that Italian? Or is that French? Or is that Spanish? Oh, it's Spanish? Okay. Yeah. Isn't the S-I yes in Spanish? C? Okay. Oh, yeah, some of you are taking Spanish, aren't you? How do we like Spanish? It's fun? All right. So, we said if carbon is present, put that in the middle. Okay. So, what column is carbon in? Okay. So, the best way to do that is like this. Okay? When there are typically 4 or less, good to just put them all the way around like that. So, how many electrons is carbon short to satisfying that octet rule? 4. Well, where's it going to get those 4 from? The hydrogens, which there are how many? There are 4 of them. So we could put one here, obviously. One here. You don't. X's, triangles, whatever you're more comfortable with using. Doesn't matter. Okay, so does carbon have 8 around it now? Yeah. So it's now chemically stable. Okay? All right. So, as we grow in number from CH4 to C2H6, again, carbon can do more than just single bonds. So, like in baseball or softball, getting past first base, maybe you end up on second base. That's a what? That's a double. Okay? Should you maybe hit one off the wall and it bounces around and you're really, really fast, go all the way past second, you end up on third, now you got a triple. Okay? Or else you could be one of them people that doesn't matter how fast you run, if you hit the ball over the fence for a home run, you can just take your time running around the bases. Yeah. Okay. And does anyone in here play baseball? No? You did? Would you be one of them that, oh man, that's going to be a home run, and you flick the bat? Does anyone know what I'm talking about? Some major league hitters do that. Sometimes they hit it, they know it's going to be gone, so they flick the bat. It's kind of showing off a little bit, I think, but maybe, maybe not. It's nice to think about baseball, though, right? Because when baseball's here, it's typically warmer weather. And I do remember watching Minnesota at Pittsburgh last spring, and it was snowing. You know, there's some snow coming down, but yet still baseball season. So, yeah. All right. So, with this, let's go ahead and do C2H6. Carbon's present, so that's going to go in the middle. So, just like what we did up there, 1, 2, 3, 4. So there's one carbon. So let's go ahead and make a single bond. See if that works. Okay. So here's our single bond so far. And notice each carbon is how many short of being chemically stable. This one is 3 short, so is that one. But as you look at what we're dealing with, you still have how many hydrogens to use? 6 of them. So we can go ahead and put hydrogens at each one of these. Okay. Are those carbons chemically stable? Yes. Is the hydrogen chemically stable? Yes. Even though it only has 1 electron to give away, each one of these carbon atoms now has 8 electrons around it. Okay. Yes. I would say it's more so covalent because you've got these 2 carbon atoms sharing that bond. And for this level, I think it's more appropriate to say that's a covalent bond. Okay. So, now, as we proceed with this next one, do you want to see the logical steps that you would take with it? Or if you want to see the logical steps you would take, then write all this information down. But if you want to just see the right answer, don't write anything down till a little bit later. Okay? The reason we say that is notice what type of bonding has taken place with with this one. So what type of bond between the two carbons? It's a covalent, but is it a single, double, or triple? It's just a single bond because they're sharing a single electron. Might be wondering, well, why does that matter? Well, again, if you only want to write the correct answer down, then I would not write anything till a little later. But the logical approach that you might take, I'm going to put them up here so we can see what it is we're talking about. Okay? So, what you might say, okay, carbon, we know that's in column 4. So we're going to do this. We're going to put our other carbon atom here, just like what we did here. Okay? But what do we still have left yet? 2 hydrogens. So you would look at that and say, well, I'm going to put a hydrogen here, and I'm going to put a hydrogen here. Put our boxes around that carbon and around this carbon. How many electrons are inside this box? 1, 2, 3, 4, 5, 6. So a single bond doesn't work, does it? It can't, because it's not satisfying that octet rule. So with some of these, if a single bond does not work, you're going to try a double bond, which would mean, okay, here's 1 carbon atom, and then there are 2 left. Then here's another carbon atom. Notice that we're forming what looks like a double bond here, and that's correct. So those lines are illustrating both of those carbon atoms are being shared between these 2. Okay? Then there's still an X here and an X here. So our carbons are done. We still have 2 hydrogens. So if we put a box around here and around here, how many electrons are inside this box? 2, 4, 6, and 1 more gives you only what? Only 7. So a single bond didn't work. A double bond does not work. So your last step then is a triple bond. Okay? And what that means is this, between 1 carbon atom and another carbon atom. It's easy to see that triple bond. That's those horizontal lines we're referring to. And whether you put them on the top or the side, it really doesn't make any difference. There's a hydrogen atom, and then here's a hydrogen atom. So if we put a box around here and here, how many are inside this box? 2, 4, 6, and 2 more gives you 8. Okay? So typically when you do these, it's best just to start with a single bond. Nope, that didn't work. Or excuse me, a single bond. Nope, that didn't work. Okay, let's try a double bond. Well, that didn't work. So let's try a triple bond. Now, not all elements can do that. For double bonds, it's only sulfur, oxygen, nitrogen, and obviously which element? Carbon. There's 4 elements we want to know that can do double bonds. Sulfur, oxygen, carbon, and nitrogen. There's only 2 elements that can do a triple bond. Obviously this is one of them, and just take a guess what the other one might be. Not oxygen. That can't do a double bond, so obviously can't do a triple bond. Nitrogen. Only 2 elements can triple bond. Carbon and nitrogen. Now, for anyone who's ever used a cutting torch, like I said, I don't know much about a plasma cutter, but when you take 2 gases and put them together to run in your cutting torch, one of them is oxygen. What's the other one called? Starts with an A. Yeah, acetylene. It's called oxygen acetylene torch. This has a scientific name of ethyne, but it's got a more common name known as acetylene. Okay? So carbon can triple bond. So when it comes to these, okay, remember, double bonds, only oxygen, sulfur, nitrogen, and carbon. When it comes to triple bonds, only nitrogen and carbon can triple bond. Just those two. All right. Left outside. Is anybody just totally lost? Are we on the bus? Left outside. Left middle. Middle. Right middle. Right outside. Okay. So, and again, if any of this isn't making sense, hopefully you have the, I wouldn't say desire, but maybe mental maturity to say, I need help, I'm going to look at this again. And of course, do you have to watch the whole thing? No, obviously not. What's nice about this is you can certainly fast forward and going through certain spots. You don't have to watch the whole thing. Okay, so the last thing that we want to do is let's go ahead and write out some of these chemical formulas. So let's say, for instance, we'll do magnesium bromide. Okay, so we're going to write out, you see the name, we're going to write out the chemical formula. Okay, what is the symbol for magnesium? What is the chemical symbol for bromine? Now, it's not magnesium bromine. Once that bromine atom has received one more electron, it becomes an ion. It gets changed from bromine to bromide. Okay, so always go by your negative ions. Bromine has a charge of negative what? -1. Magnesium then has a charge of positive what? You always write your positive ions first. Positives come first, then negatives. Okay, so these two do not add up to 0, do they? No, they do not. So what's not the least common factor, we want the least common what? Multiple. In other words, what's the smallest number that both of these can divide into? Okay? And again, the answer that you get from that division tells you what to put below. So, 2 divided by 2 is what? Got 1 here. 2 divided by 1 gives you, and again, that's not a value of -1, it's just a charge. Those are two totally different concepts. I understand you're going to say, well, 2 divided by -1, we learn in algebra is -2. Well, that would be correct, but it's just the charge, not the value. Okay. And another aspect that we start with this chapter is adding together the atomic mass or masses of these compounds, which would mean, okay, magnesium has an atomic mass of what? 24.31 then, we'll round to the nearest 100, plus, what's the atomic mass of bromine? 79.92, and how many of them do we have? So we take that 79.92 and multiply it by 2, okay? So 79, okay? So 151.18, okay? So you just add them two together then, and that would give you your atomic mass for magnesium bromide. It's just simple addition. The reason being is, again, some of you freshmen had came in and saw juniors taking a problem quiz over what we call stoichiometry and adding together. You might think this is simple, but, and for the most part, once you catch on, it is. But if you go too fast, chances are you're going to make mistakes. That's nothing, it's not a derogatory comment upon yourselves, okay? It's just, for instance, human nature. All right. Then the last thing that we'll do today, get a little more complex with a polyatomic ion. We've said what they are. Someone give me an example of a polyatomic ion. They're on page 3. Someone give me an example of a polyatomic ion. Okay, and that's called what? Carbonate. Okay, so with that, we'll go ahead and say, so you want something that's medium, or you want something that's kind of a little more difficult? And since we're working on it together, maybe something a little more difficult. Okay, so we'll go ahead and say this. Oops. Okay. And this is a fairly difficult one because I'm just curious how many of you on your tables on element 25 told you to write something. So chances are, if you, why would we do that? Does it say +3 on your element boxes on your tables? No, but what does it say on this big periodic table in element 25's box? It says +2, +3, and 7. So it doesn't say +3 on your charts, but it does on this one. So we had told you individuals, please write +3 in manganese's box. Because, well, how would you know which charge of manganese to use? Well, if you know your Roman numerals, this is which Roman numeral? 3. Okay? So, what is the symbol for manganese? Mn. Not Mg, because that's magnesium. Okay? Then, you had picked the carbonate ion. That's got a formula of what? CO. Okay? So, what's the charge? Always go by your negative ions. Negative. -2. Okay? What's the charge of this manganese? Okay? You can look at that table, but you don't even have to do that. What does it tell us right here? It tells you that right there, that it's a +3 charge. Okay? Now, what's significant about them two charges? Does that add up to 0? No, it does not. What is the least common multiple that both of them would divide into? 6. It's not 3 and it's not 2, because yeah, you could put a 3 here, but by the time you do that, does that give you a nice whole number when you divide 3 by 2? No, it gives you 1.5. We don't want that. So when you correctly choose 6, okay, what is 6 divided by 3? So what do we have to do with that 2? Put it after the end. Remember, the answer that you get tells you what to put below. Alright? Now, 6 divided by 2 gives you, now, some people may forget to do this, but we want to look at this and say, we don't want one carbon in 33 oxygens, because that's what it looks like right now. We want not just one carbonate ion, we want 3 of them. So what happens is you put that in parentheses then. Okay, that's like we said, let's do one that's probably a little more difficult since we're working on this together, because you're going to be responsible for this information probably by the end of this week. Okay, because again, I myself, I'm looking outside. I didn't think it was going to be snowing at all this morning, but I think we got one front coming in after another. Okay, so that's why we're kind of going a little faster. But if you have problems with this, you can always go back and say, well, why did I write this 3 here? Why did we divide by 6? Well, we divide by 6. Well, then why do we put that 2 down there? You have that opportunity to go back and see why you wrote certain information the way you did. Then the last thing you would want to do is take manganese, which is what, 54? Okay, so 54.93 times 2, okay? What does it mean to distribute? So we're going to, well, it doesn't necessarily have to be yourself, but our point guards can't handle the ball. They can't handle the pressure. We're going to make you point guard. Is that a promotion or a demotion? There's our point guard. So what does it mean to be a point guard? You bring the ball up the court. So if you are distributing the ball, are you passing it to the same person? No. You're spreading the wealth, if you want to call that. Because some people like to tell that story that I never... Who can I pick on? Okay, so Austin says, I'd never pass that ball to a young gentleman there because I'll never get it back again. What does that mean? That chances are you pass it to him and one of 2 things is going to happen. He's probably going to do what? Probably shoot it. Don't pass it to him because he's never going to pass it back. So is that true? So, oh, sometimes. Okay, so fair enough. So when you are distributing the ball, it just means you're going from one player to another. You're spreading the wealth. So what do you suppose you got to do with this 3 to what's inside the parentheses? Distribute that in, are you adding or multiplying? You're multiplying. Okay? So what's 3 times 1? 3. So carbon has an atomic mass of 12. 12 times 3 gives you 36. Okay? You have 3 oxygens, but you got that 3 on the outside. So what do you do with those 2 numbers? What do we do with these 2 numbers? Is this 6 or 9? 9. You multiply the 2. So we take 16 times 9, not times 6. So each oxygen is an atomic mass of 16. We have 3 of them, so that would be 48. Okay? But then we could say take that 48 times 3. We get the same answer. Or 16 times 9, whichever you're more comfortable with. Okay, so we will probably pass out that first worksheet. It said we're going to do that tomorrow, but I'm going to pass it out at some time later this afternoon when you're all together, which is it English class, or have you had that already? Okay. So when you're all together, I'll go down there, and I'll probably put some examples on there from the Science Channel. So just in case we don't have class or school, you have that opportunity to go back and read that information. We'll pick up with this next time.